All right, everybody, hello and welcome back. Today we're going to talk about exponential functions. So we've got two examples here, one on the left and one on the right. We're going to start off on the left-hand side with f of x is equal to 3 to the x power. Now, we know that this is an exponential function because our variable x is in the exponent. That's what makes it exponential. Now, this value right here is called our base. The base is the base of the exponent. It's the bottom part. Now, our base is always going to be greater than 0. That means it's always going to be positive. We don't have negative bases, so if there's a negative, that means it is going to refer to the transformations that we'll talk about a little bit later on in our unit. Now, our base value, again, is going to kind of have a big impact on what our function looks like. So if we think about our table here, like we've done in the past, we can pick some nice x values to go ahead and plug in. Now, most people are going to choose numbers such as these, which are great choices, right? We've got the left side, the middle, and the right side of our coordinate plane. So if I were to take these and plug them in, all I'm going to do is I'm replacing the x value with the x values in my table. So I will have 3 to the negative second, which is 1 over 3 squared, or 1 over 9. I'll have 3 to the negative first, which is the same thing as 1 over 3 to the first. I have 3 to the 0 power, and anything to the 0 power is 1. 3 to the first is 3. 3 to the second is 9. So I can go ahead and plot these points. Now, I'm not going to be able to graph 1/9 on my y-axis perfectly, so I'm just going to estimate here. So we have negative 2 and 1/9. We have negative 1 and 1/3. 0, 1, 1, 3. And then 2, 9. So this is what our function is going to look like. Now, if we wanted to add more points, we could. But what we would see is a function that looks just like this. One very important fact about exponential functions is they have what we call a horizontal asymptote. This one just happens to be at y equals 0. Now, horizontal asymptote is an imaginary line that basically blocks our function from passing through. So if you take a look, our function kind of levels off here, but we never end up going to the bottom half of our coordinate plane. Well, the reason that is there is no x value that I can plug in here and get out a negative. So mathematically, it just doesn't happen, but what that means is we're going to get closer and closer and closer to y equals 0, which is why we have a horizontal asymptote. Now, all exponential functions have horizontal asymptotes, and they will move depending on the transformations that we have, but the parent function is always going to be at y equals 0. So we can then do our domain and range. Excuse me. The domain is left to right, so if we look on the left side of my graph, I've got an arrow pointing that way, so we should continue in that direction towards negative infinity. And then on the right side, we start to move up, but we can't forget we are also moving to the right. So what that means is we're going to continue to move up, but also continue to move to the right, to the right, to the right, all the way towards our positive values of positive infinity. And now they get parentheses because we can't count to infinity. They're not included, so they get parentheses. Now the next part is going to be our range, which is the up and down, right? Our y values, our outputs, in this case, our f of x values. So the lowest value that our function goes towards is this asymptote. We start to get really close to it. Now, we don't ever touch the asymptote. We get closer and closer and closer as we move to the left, but we never get to 0. Again, because there's no value that I can plug in to my exponent that will make this function equal to 0 or less than 0. So we've got 0, and 0 doesn't get to be included because we never officially get there. And then as we can see, we also end up moving all the way up, which is going to approach infinity. Now, the nice thing about exponential functions is their domain is always negative infinity to infinity. Not only can we get the domain by looking at the graph, right, left to right, But think about domain as what x values are we able to plug in. There is no restrictions for exponential functions, just like there's no restrictions for linear functions. You can plug in whatever you want, and therefore our domain will always be negative infinity to infinity. Let's move on to our next one. So the next one is a little bit different, but pretty similar idea here. Again, we're going to pick some good x values. Now, we should know what the shape of exponentials are, right? They are curves. And now it might look like this. It might be like this or reflected this way. It's probably not the best drawing there. Reflected something like this. Maybe something like this. But the idea is these are all curves, right? We should know what these look like. We've seen them before. So we really don't need all of these points. We only need two of them, really. And those 2 points, those two x values we're going to want to plug in are going to be 0 and 1. And the reason that is because anything to the 0 power is 1. And then anything to the first power is just itself. So again, all I did is I took these values and I plugged them in for my exponent. So I've got 0, 1, and then I have 1, 1/4, which is right about there. And so we can kind of see if we were to connect these, we should be able to figure out that our trend is going to continue in both directions. And we're going to look just like this. All right, this is basically how we are going to graph all exponential functions. We really only need 2 points. And although you could use whatever 2 points you want, using x values of 0 and 1 are going to make this the easiest. So we can't forget that we have to throw in our horizontal asymptote, that imaginary line that our function does not cross. And again, it's the same idea. There is no value that I can plug into my exponent here that will make g of x become 0 or anything negative. So our domain, as we just mentioned before, is always going to be negative infinity to infinity. And now our range, this is going to change, but it actually just so happens to be the same range as over here. If you take a look, the lowest value we start to get closer and closer to is 0, but we never really get there, so it gets a parenthesis. And then we have an arrow pointing up towards infinity. So these are 2 exponential functions. As you can tell by their pictures, they are pretty different. Not only did I graph them a little bit different, but if I were to... that makes them a little bit better. But as we can see, one of them seems to go up from left to right, and the other seems to go down. And that's because the one on the left is exponential growth, and the one on the right is exponential decay. Now, what makes it growth is, as you can see, our x values, as they get larger, so do our y values. And the reason that is, that's because our base value, in this example, is greater than 1. What that means is our values should be multiplying by a value greater than 1. In this case, it's 3. So we read a graph like we read a sentence. So starting on my left side here and moving to the right, we could see that this is going up. So we say that this is exponential growth, is growing. Contrary to the other one, this one here is starting to go down from left to right. And the reason that is because it is exponential decay. Now our base value here is less than 1, which means the value we are multiplying by, sorry, this should be a 1/4. In our table, when we look at our output values, is smaller than 1. That means our values are getting smaller. So for example, the next one here would be 1/16. If we were to do it again, we'd have 1/64. These are all getting smaller and smaller and smaller because our function is decay. All right, so exponential functions have x in the exponent. They are typically made up with a base value, the variable in the exponent, and sometimes there's some other things around there. However, we can determine if they're exponential growth or decay by trying to see if the base value is greater than 1. If it is greater than 1, then that means our values are growing, and it is growth. And if it is less than 1, that means they're getting smaller, and it is decay. Now, when we look at equations like these, we can actually figure out what our growth and decay rates are. So let me give you an example. We have L of x equals 2 times 1.50 to the x power. Now, we've got a 2 in front, but the important part here is our base. Remember, the base determines if we're going to be growth or decay. Well, typically what we like to do is we separate that base value to 1 plus or minus whatever our ratio would be. Well, this is 1.5, and so therefore our R value is 0.5. Now, I knew this was a plus because this is greater than 1. The reason we have a 1 in here is if I multiply something by 1, it stays the same. So it's either going to be 1 plus a number if we are growing, or 1 minus a number if we are decaying. So we can rewrite base values to look similar to this so that we can very easily determine how much this is growing by. Now again, the 1 represents itself, so anything times 1 doesn't change. Therefore, our 0.5 is going to represent our growth. Well, 0.5, what we want to do is we want to convert this to a percentage to see what percent we are growing by. So what we could do is we could multiply by 100 and we get 50. So we would say that this has a growth rate of 50%. We are growing an extra 50% every time. And that's because of this base value. So we have another similar problem right here. P of x equals negative 3 times 2 to the x power. So again, we got some other stuff going on in front here, but right now we're only concerned with our growth or decay rate. Well, if we look at our base, this is growth because it is bigger than 1. Well, how much are we growing by? So what we can do is we rewrite this. So we have 1 plus or minus some number to the x power. Well, hopefully we know 1 plus 1 is going to give us 2. This 1 stands for the initial value, and then the extra 1 is how much we are growing by. So again, we're going to take this and we are going to multiply by 100, and we get 100%. So we say we have a growth rate of 100% for this exponential function. Now, these are all growths, but we also got some examples of decays here. Exact same idea. We still have the negative in front. We're not really worried about it right now. Instead, what we're going to do is we're going to start with a 1, and now our base value is less than 1, so I'm going to subtract. Now you think about what am I going to subtract to go from 1 to 0.75, and the answer is 0.25. What that tells me is I can convert this rate to a percentage by multiplying by 100. And we should notice that this is less than 1, so we are decreasing. So we say that this has a decay rate of 25%. Now, our last example for a problem like this is a value just like what we did in our warm-up when we graphed. Exact same idea. Rewrite it 1 plus or minus a rate to the x power. Well, hopefully we should realize that 1/2 is less than 1, so we are subtracting. And again, we are subtracting 1/2. So if I multiply that times 100, we get 50% as our decay rate. All right, and that's important because we're able to describe what is going on in specific situations. So let's say this was a word problem, and maybe this one's a little bit better for a word problem. Let's stick with this one. All right, we're saying a population is described by this equation. Well, what this equation tells us is because our base is less than 1, we are decaying. That means the population is getting smaller. So we'd want to know for every what year, for every 1 year, how much are we decaying by? And the answer is 50%, which is why we rewrite. And now, again, what we like to do is we take these and we rewrite them so we have 1 plus or minus our ratio to the x power. Now, the a value typically stands for our initial amount, and our R value is our rate as a decimal. Typically, the exponent is going to represent time. Sometimes that changes. It kind of depends on what type of model you're looking at. Now, for our last problems here, they're a little bit different. So if we look at this one, we should be able to tell that we are growing. So this is exponential growth. However, our exponent is different. I've got my x value divided by 2. So in an application problem, we would say that, again, this is our initial amount, this is our rate, and then our exponent typically represents time. So if this is time and we're dividing by 2, time is usually going to be in years, and again, the problem might specify, but this would be every 1 year divided by 2, or half of a year. Well, we know what half of a year is, 6 months, but in other examples like this, we have 1/5 of a year, which isn't that easy of a number to calculate. When we're talking about how much we're growing or decaying by, we want it to be for every 1 year, or whatever value of our exponent is. Essentially, we want to use exponent properties to rewrite this so we are able to simplify and get our exponent alone in the exponent. So what we're going to do is I am going to essentially separate the 1/2 and the x. I am breaking them apart because, right, we could simplify to go that way. And now what I can do is I can take this and I can group together the 3 and the 1/2. All right, so this is basically the opposite. Technically, this is our power property, where most of us would go from here to here, where we are simplifying, but now we are separating, and again, it's so we can get our x value by itself. So if I just plug this into my calculator, again, we're not really worried about that 2 in front right now. So I've got the 2, and then I have 3 to the 1/2 power, which is going to be approximately 1.73. Now, the reason I would do this is now I have just x in the exponent. So I can figure out that my growth rate is 73% for every 1 x value. And again, most of the time that is time, so it's going to be in years, but it could be different depending on the problem. It makes more sense for us to give a growth or decay rate in terms of 1 unit of our exponent. It makes more sense for us to say it grows by 73% every year than every 1/5 of a year. So we use exponent properties to do that. Real quick, this one's exactly the same except we have exponential decay. So this would be rewritten with a negative in front, 1 minus 0.2. Well, we don't need to do that just yet, right? Because we still have our value in our exponent. So what I'm actually going to do is I'm going to do that rewriting -1, 0.8, 1/5, and x. And again, I'm just going to group together my base in the exponent to simplify. So I have a -1 in front. We have 0.8 to the 1/5 power, which is about 0.96 to the x. So that tells us that our decay rate is 4% every year. And how I did that is 1 minus 0.04 is the same thing as 0.96. All right, so just quick recap here. We can find our growth and decay rate by determining how far from 0 our base is. And now we can only do that when our exponent is by itself. So if it's not, we need to separate it. Okay? As always, thank you for listening. If you have any questions or concerns, please feel free to reach out. Thank you.